So in this video, I'm going to be introducing you to geometric series. Now, geometric series they should be pretty obvious to you because you might have learned them before. You might have learned the geometric sequence and getting terms in the geometric sequence. It's the same idea except it's a series and you're adding stuff together. And when you go to calculus, you learn adding infinitely many terms together. And geometric series work very well because they have a certain form and you can find the sum very easily with certain values. And so I'll show you what I mean when I say that. And basically, so let me give you an example of a geometric sequence, right? And this is not going to be very difficult. So it's 1, 2, 4, 8, 16, and then 32, and then 64, blah blah blah, right? So what's going on here? What can you see? Clearly there's a pattern. You can obviously see that, but the pattern is you're multiplying by 2 each time you go to the next term. Look at that. You're multiplying by 2 to get to the next term. That's what's happening throughout the entire sequence. Now, if you go ahead and take the summation of this stuff, all of this stuff, you get essentially a geometric series. That's what you're talking about when you talk about a geometric series. So you've learned geometric sequences before, and it's just adding stuff together. And when you add infinitely many terms together, you have, of course, the infinite series. So let's go ahead and give you the general form of a geometric series. So this is geometric series. So here's the form. So if you have the sigma notation. You have sigma from n equals to 1 to infinity, and you have a times r raised to the n minus 1 power. What does this represent? Well, let me tell you. Basically, this a that you see here represents the first term in your sequence, essentially, your first term. So in this case, it would be 1. In this geometric sequence, it would be 1. Now that's what this represents, their first term. Then you have your r, which you should know. That's your common ratio, basically the number 2 here. You're multiplying by what each time? And then you have n minus 1. N minus 1, basically, when you keep counting up and you have n equals 1, n equals 2, you basically raise this to the power of n minus 1. So let me expand this a little bit. So let me expand this here. This is basically equal to, so let's see. When n equals 1, we have, this is 1 minus 1, which is 0. So this whole thing is just 1. So you end up with a. And then when n equals 2, so you add this to n equals 2. When n equals 2, you just have a times r, because this is 1. And then n equals 3, you have a times r squared. And then when n equals 4, so you have this, right? When n equals 4, you have this. You have this. It just keeps on going. It's a pattern. So this is when n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, so on. And it should make sense to you. Does this fit our pattern that we see up here? Let's see. Let's try to write a geometric series representation for adding up the terms of the sequence. So let's go ahead and do that. So we'd go from n equals 1 to infinity, and then our a is our 1. We said that before. And then we have our r, which is 2. We said that also before. And then n minus 1. Does this work? Let's see. This could work, right? Let's see. When we have n equals 1, we end up getting positive 1. Okay. And then we have plus, when n equals to 2, we end up obtaining the value, let's see, n equals to 2, we have 2. Okay. N equals to 3, we have 4, and so on and so forth. That's exactly what we have up there. Basically, what you're doing is you're taking your sequence. This is your sequence. This can be written as a sub n, which is actually just, so your a sub n is actually your, for a geometric sequence, it's just a times, well, you could write it as a, that's your first term in your sequence, and then times r raised to the n minus 1. This is a form that you can represent it in. Now, keep in mind that you do not have to represent it like this. You don't have to represent it in this form. That's one form, or just in this form. There's multiple forms to represent it. And you can also represent this geometric series as in the following form. So if you go from n equals to 0 to infinity, you end up getting a times r raised to the n power. This is also an equivalent form to represent it in. So if you wanted to expand this, you can. This would just be a, and then plus you have 1, which would be a times r, plus a times r squared, plus a times r cubed, and you end up getting this when n equals to 0, n equals to 1, n equals to 2. So you actually get the same exact stuff. You get the same exact stuff. And this is, so notice that this is the same thing. This is the same thing as this. So it's the same exact stuff. It's just in a different form. And since you started with 0, you're essentially you're adding 1 to your n value, and that's why you have n plus 1 minus 1, which is n. So that's basically what you're obtaining with this. Okay, so that's just an introduction on these stuff, on how to represent a geometric series. It shouldn't be too hard, honestly, if you already know stuff about this. Now let me go ahead and delete all of this, and let's go ahead and see when we can determine convergence or divergence of a geometric series. Convergence basically means we're converging to a certain value, we're approaching a certain values, we add all these terms up. Divergence means we are not. We are going to infinity or negative infinity or something like that. So we're not converging to a value. So let me go ahead and rewrite my expression. So this is a summation when n equals to, I'll use the 1 to infinity form. So a times r raised to the n minus 1. Now this series converges, so you should write this down, converges when your absolute value, when the absolute value of your common ratio is less than 1, or this is equivalently written as, if you don't like the absolute value, which I personally don't, you can write this as this. So it's between -1 and 1. That's what it is. Now, this is what you have here. But if you want to determine divergence, so this, if you want to determine divergence, it diverges when, of course, when it's not less than 1, the absolute value of r is not less than 1, your absolute value of r is greater than or equal to 1. So an equivalent way to write this, if you wanted to, would be when your r values, well, I think I'll leave it like this. When your absolute value of r is greater than or equal to positive 1. Basically, when you have when your r is not in between a -1 and 1. That's basically what it is. Of course, non-inclusive. You're not including the -1 or 1. Okay, that is what you have for this convergence or divergence of a geometric series. Now, the one thing I'll write down here, if you want to determine the sum of an infinite geometric series, the sum is basically, so again, I'm going to rewrite this again. So n equals to 1 to infinity. So this entire sum would be equal to a divided by 1 minus r. This thing here represents your sum. That expression here, plugging in your value for a, plugging in your value for r, you can get the sum of this infinite series, assuming that it is, of course, convergent. So that is a nice expression that we can use, and this is very important when you get into power series, talking about how you can have a value for x, and you can rewrite it as a function, and your function is representative as your series, and then we get into Taylor polynomial, or Taylor series, Maclaurin series, Taylor polynomials, all these interesting stuff. But it all starts with this general expression, this general equation, this general idea that we have here, and then we can expand from there. We use derivatives, integrals, and stuff like that. But that's important. Let's go back to our previous example now. I'm going to erase all of this now. Hopefully you wrote it down. Let's go back to our previous example. So our series was, let's go write this again. N goes from 1 to infinity. We have 1 times 2 raised to the n minus 1, which was, of course, if you wanted to expand the first couple of terms, you could write this as 1 plus, and then you'd have 2, right, plus 4 plus, so this is when n equals 1, n equals 2, n equals 3, n equals 4 would be, so this would be 8, and then that's what you would have. Now, if you wanted to determine the sum, first of all, let's determine if it's convergent or divergent. That's important. You take this R value. This is your R value, so your common ratio. Take the absolute value. So absolute value of 2, which we don't need. It's just 2. Is this less than 1? Or is it between -1 and 1? No. Is it greater than 1? Yes, the absolute value of 2 is greater than or equal to 1. Which means, of course, 2 is greater than or equal to 1. Which means that we are actually not convergent, we are divergent. So this series, this infinite series, it diverges, it's divergent. You will not obtain a number, you will not obtain a nice number. But if we were to say, for example, our series going from 1 to infinity, and you know what, I'll use the, that's fine, let's just keep it like this, 1 to infinity, and we have, let's say, for example, 2 times 1/2 raised to the n minus 1 power. What would this be? Well, let's try to just expand it a little bit. If you want to, you don't have to. So when n equals 1, we have 2. When n equals 2, we have 2 minus 1, we have just 1. When n equals to 3, we have 2 times 1/2 squared, which is 2 times 1/4, right? 1/2 squared is 1/4. And then this would just get you to 1/2. Notice that the values are like, it looks like it's converging to some value. Looks like it. But although you shouldn't just quickly zoom it, you should check. So let's check. It's convergent when your R value is between -1 and 1. Is this between -1 and 1? Is 1/2 between -1 and 1? That is true. Since it is true, we can prove that we can say that this is convergent. This is convergent. Okay, you might be wondering, what does it converge to? Oftentimes you cannot determine that, but for a geometric series you can. Basically, it converges, the sum is, so a sum converges to a value, the sum converges to a value, so sum is equal to the value here, so it's n equals 1 to infinity. If we wanted to get this equation that we were written the previous screen up previously, oops, this is equal to a divided by 1 minus r. Your a here is 2, so this is your a, this is your a, and this is your r, this is your r, this is your r. So if you were to just write it out, you would just get this in the form 2 divided by 1 minus 1/2. Right, let's just double check. 2 divided by 1 minus 1/2. This is, of course, 2 divided by 1/2, or, of course, that's just 4. So that's the sum. That's literally the sum of this infinite series. So if you add up this series, you add it all up, you add up all the terms, infinitely many terms, you end up converging to the value positive 4, which is pretty interesting. Pretty interesting. Okay. So let's do another example, but let's do it in the form n equals to 0 to infinity. And so this, let's say it was just 1 times, let's just say 1/2, let's do 1/4, 1/4 raised to the n power. So let's try to expand this a little bit. So n equals 0, we have just 1. N equals 1, we have 1/4. Right, n equals 1, we have 1/4. N equals 2, we have 1/16. N equals 3, we have 1 over 4 cubed. 4 cubed is 64. 64. Okay, again, it looks like it's going to a certain value, but we'll see here. Or it looks like it's getting smaller and smaller, approaching essentially 0. And that could tell us that we are essentially going to converge. Our series is not going to go to infinity or negative infinity, sum. But we'll see. We have to check. So it's convergent when this value is between -1 and 1. Is it between -1 and 1? 1/4 is indeed between -1 and positive 1. -1 and positive 1. Since this is true, this is a convergent series, convergent geometric series. So convergent geometric series. Let's determine the sum. So the sum, of course, now this is the form we had our sum in, if you remember. So a times r raised to the n minus 1 power is a over 1 minus r. This is what we have to use. But remember, we can't just plug in our a and our r. You can't just say that this is your a, this is your r, because it could be that it isn't. This, of course, is your r. This is not changing, so you can, of course, plug that in for r. But your a, this is not your a. This is not your a. Your a is actually something else. The reason why is because we wrote it in a different form. So we'd have to convert it. So this n equals 0 to infinity. So this is 1 times 1/4 raised to the n. This is equivalent. So if we wanted to get it to the n minus 1 form, what should we do? Well, we have to think a little bit. We have to try to rewrite this in a certain way. So if we were to write this here, this stuff here, as 1/4 raised to the n power, n minus 1 power, and then you multiply this by 1/4, what would happen? 1/4, I guess you could say raised to the 1 power. This would be 1/4 raised to the n minus 1 plus 1 power. This is gone, so you end up getting 1/4 raised to the n power, which is exactly what we had here. And so you can actually write this here as this. So this is equivalent to, you can go from 0 to infinity. We have 1/4 times 1/4 raised to the n minus 1 power. Does this still get you all of this? Well, let's see. So if you see here, we have 0, we have negative 1, so 4, and then 1, yes. 1, we have 0, so it's 1/4, and yes, it does. But it's more importantly, it is in this form, which is exactly what this is in. Since it's in that form, we can use the a over 1 minus r. This is your a, and this is your r. So if you were to use a formula, it would just be 1/4 divided by 1 minus 1/4, which is equal to, so this is equal to 1 minus 1/4 is 3/4, and so this is 1/4 times 4/3, cancel, this is 1/3. That's the sum. So the sum of this, where is that? This infinite series here is just 1/4. It's pretty nice. And that is geometric series. Those are geometric series. There's a lot to learn with geometric series, but really understanding geometric series helps you solve a lot of problems when you deal with power series, which is a harder topic, in my opinion, in the future. So this is important to understand. So that's geometric series.